We're here in Hawaii to test a mission we call Resolve. And Resolve is designed to go to the poles of the moon and search for water ice and help us understand the horizontal and vertical distribution of the water ice that we now know is there from the LCROSS mission back in 2009. So we came here to Hawaii because this is a perfect lunar analog. The moon has a very volcanic origin. When you look at the moon at night and see the dark areas on there, we call them mare, they're a lava flow. And we've come to Hawaii because Hawaii is a volcano. And we have lava flows, but not just flows, not hard rock lava, we also have a lot of volcanic ash. And that's what we were looking for. The volcanic ash has a soil size distribution that is very similar to the moon. Even has even a chemical makeup that comes closer to the moon than some other places. It's not perfect, but it allows us to test the hardware as best we can in an environment and do an actual mission simulation end to end. With a control room, remote operations, and even lunar time delay. Resolve is a partnership between NASA and the Canadian Space Agency. The Canadian Space Agency has provided us with a rover to carry our experiment package, named the Artemis Junior. And they also provided a drill that will collect a subsurface sample for us about 1 meter deep into the lunar soil, and some of the avionics equipment as well. NASA has provided a neutron spectrometer, which will be like a divining rod that will help us search as we drive around on the surface and see if we can find subsurface water. And near-infrared spectrometer that helps us find any surficial water that might be there that has been seen by some orbital missions. And a gas chromatograph mass spectrometer that will actually allow us to quantify not only the water that we find on the moon, but the other volatile elements that LCROSS saw, things like ammonia, methane, carbon monoxide, other things that we expect to find frozen in the subsurface of the lunar soil. Analog missions in general are very difficult to pull off. You've got hardware that is being developed all over the country, even internationally. And so first we have to get all that hardware to one place and integrate it. This year we integrated all that hardware in Florida. Some of the last pieces didn't show up until about 3 weeks before the test. Then it all has to be crated up and shipped. We're shipping things that are hazardous, like lithium-ion batteries. So there's all kinds of permits that must be obtained, and we really had some challenges getting our batteries. At one point, we even thought we might have to disassemble the batteries into individual cells, ship the individual cells, and then reassemble the battery when they got here in Florida. Once you get here, we are in a harsh environment, so it requires four-wheel drives to arrive in these places, all-terrain forklifts and things of that nature to help us lift and assemble the things in place so that we can begin our simulation. The timeline for this mission is probably tighter than any surface mission NASA has ever attempted, at least with the mobility system. We will have 5 to 7 days of sunlight on the moon to execute this mission. And then when the sun goes down, since it's a solar-powered mission, the hardware will probably get so cold that the electronics won't wake up again when the next month rolls around and the sun comes back up. So to be sure that we're ready and can actually achieve the objectives of the mission, it's very necessary for us to see if we can really achieve this. We don't want to send the mission to the moon and then find out, that it was too aggressive of a timeline and we didn't achieve our goals. So that's one of the primary reasons for this. It is a hardware test, but it is really a mission simulation to put the team into an environment where they have to struggle like they would on a real mission.